It's good right now. Other classes have. Oh, and environmental. This is. Oh, yeah, one. It wasn't four.
You get 2 equations. 2 equals that was oh, I don't know. But I don't know.
So. That crying. Is that right? And 10 years should be in. Maybe what I was doing, just actually something. Down you, that's what I'm ready. It's on you. Yeah, I'm not. So, okay. You don't study like a student. Why? Only because I used it all. Because when I went to the competition, I didn't use like I got like it was a certain it was like 50 gigs or something like that. I had to use the bicycle a little lot because the reception over there is. Even though they have like the rules of Wi-Fi for the competition, since everyone's using it, it's just like to go. Next time, we need to get to the Wi-Fi. Yeah, everyone Wi-Fi as well. Not, I don't know how many programs on that. So, yeah. Awesome.
All right, it's 4 o'clock. Let's go and get started. All right, good afternoon, everyone. How's everyone doing today? Good. Hopefully everyone's staying dry. It's I think they would say this is the biggest storm so far this year. But you know, if you've lived in California for any amount of time, you know that any rain is good. You know, especially after all the fires we're having. So this is great. But you know, stay safe out there, you know, drive safely. If one thing, Californians don't really know how to drive in the rain, so make sure you guys are staying safe out there. Okay. So for today, today is just going to be a continuation of what we started talking about on Tuesday. So Tuesday we introduced this idea of the Laplace transforms. So we're going to continue on with that. We're going to do a lot of practice today with taking forward transforms, inverse transforms, especially the inverse transforms. Those are going to be a little bit tricky. And then hopefully, I'm hoping that we can work our way up to, you know, solving differential equations with Laplace transforms today. Okay. All right. I think that's it. I don't think there's anything else I have to say. Are there any questions I can answer before we get started? Okay. All right. So let's continue where we left off. Okay. So on Tuesday, we introduced this idea of a Laplace transform. So Laplace transforms kind of belongs to a family of mathematical techniques, which we call an integral transform. And so what that basically means is that you're going to be performing an integral to perform this transform. And the idea is to basically perform a change of variable. So we're going to change the main independent variable from the physical domain to the Laplace domain. Oh, sorry, did my mic cut out again? Oh, it says it's going. Can you guys hear me on Zoom? Okay, good. Okay, so we're performing this change of variable. So basically, when we have a function f of t, okay. So this f of t represents a function in the physical domain. Where t here represents your physical domain variable. So in this case is time. Okay. When we perform our Laplace transform, we're going to get the same, basically the same function here, but represented with a different set of variables, okay? Or I guess different variables, singular. Okay? So kind of the notation that I use in this class is that if I'm using a lowercase letter, that's going to denote a function in the physical domain. Most of the time it's going to be time. And then an uppercase letter will be the same function in the Laplace domain. Okay. Okay. So that's kind of all we've talked about so far is how to take a function and then transform it into the Laplace domain. Okay. So last time we spent I think probably most of the time talking about the actual formula that you can plug in, right? And so what we said was f of s is equal to integral from 0 to infinity of f of t e to the minus st dt. Okay, so that's technically the exact formula that you use to perform the Laplace transform. But in reality, in most practical cases, we're actually not going to use this formula. But it's good to know where it comes from. Okay. Okay, so practically, okay. Not that there's anything wrong with the formula, and so you definitely can use the formula. It's just it's just a little bit time consuming, especially when you see eventually kind of what we're going to use it for. Okay. What we actually do is we actually look up a table of these Laplace transforms. Okay. So for a lot of common functions, especially the functions that end up coming out of our differential equations, a lot of those have already been tabulated for us. And so this kind of process of performing the Laplace transforms is actually quite simple. Okay. And so we actually wrote down the table kind of end of class last time. So let me just scroll up just a little bit. All right, so this should already be in your notes. But if not, there's going to be a table that's posted online as well. So I'm going to post this on the Canvas site. So don't feel the need to kind of write this down really quickly. It'll be in the it'll be available for you. Okay. So basically, the way to use this table is that if you need to take a transform of t squared, okay, you just look it up in the table and then you just put in 2 over s cubed. Okay. And the good thing about this table is that, these are all functions that you're commonly going to see when we're solving our differential equation. So we have our polynomial terms here, we have our exponential terms, our sinusoids, and 99% of the terms that we're going to be dealing with kind of fall into these categories. So these are all, really useful for them. Okay. Because remember, the whole reason we're kind of going down this route, we're not just learning Laplace transforms for fun. The whole reason we're learning this is to give us an alternative way to solve differential equations. Okay. And some people may find this beneficial because by performing a Laplace transform, we'll be able to solve our differential equations using algebra. So it essentially turns our problem into an algebra problem. Okay. Okay. So whether or not using algebra is better or not, I'm not going to accept that judgment onto you guys. I'll let you guys decide. Depends on how you feel about partial fraction decomposition. But it is an alternative way, and it does allow us to solve for different types of problems that we couldn't do before. And so we can make use of step functions and impulse functions, which are two different kinds of modes that we previously couldn't do before. Okay, but this was just a recap from last time. So, from here, I wanted to do some examples of performing Laplace transforms and doing inverse transforms as well. Okay, so I think doing inverse Laplace transforms is something you just kind of have to practice a lot. So we're going to do plenty of examples of that today. But before we do that, are there any questions on this? Okay, all right, so let's do some examples. So let's take a couple Laplace transforms with the table. Okay. Okay. So the important thing to remember when you're taking Laplace transform and inverse Laplace transforms is that the Laplace transform is a linear operator. So that means any constant term that's in front, anything that's broken up by plus signs or minus signs, you can kind of break those up into smaller, kind of more bite-sized chunks. Okay. So take advantage. So that's kind of the main trick to Laplace transforms is taking advantage of this linearity to kind of factor some terms out. Okay. All right. So let's do a very simple one first. So let's say f of t is equal to 9/2 e to the 4t. Okay. All right. And so we want to let's find the Laplace transform of this function. Okay. So right off the bat, we see that we have an exponential function here. So we have e to the 4t. So that's good. Okay. But we also have a 9/2 in front. So first thing I'm going to do is let's form the Laplace transform. So we're going to take the Laplace transform of f of t. Okay. So remember, I use that kind of fancy looking L to denote a Laplace transform. Looks like an L that's made of a long piece of spaghetti. Okay. So we're going to take the Laplace transform of this function 9/2 e to the 4t. Okay. So if you go back to our table of Laplace transforms, we don't have a table value that's this exactly. But we do have a table entry for the exponential, right? So we do have a table for entry for the exponential, but not for the 9 halves. Okay. But luckily for us, the 9 halves is just a constant coefficient here. And so we can just factor it out of the Laplace transform, taking advantage of that linearity property that we just talked about. So let's take this 9 halves, let's pop it out in front. Okay. So you have 9 halves, Laplace transform of e to the 4t. Okay. All right, so now we can just use the table from here. So there's no need to use the formula. So if you scroll back up to the table of Laplace transforms, you can see that we do have a table entry for e to the at. Okay, and so the Laplace transform of an exponential function, given that a is a constant here, is 1 over s minus that constant. Okay, so let's apply that here. Okay, and so the Laplace transform for this is going to be 9 over 2. So that's a constant that just kind of comes along for the ride. And then Laplace transform of exponential for t is equal to 1 over s minus 4. Right, and then you can just kind of leave it like that. Okay. So very simple example first, if you have a constant that's out in front, it just comes right out of the Laplace transform. So you just take the Laplace transform of whatever functions is there. Okay. Any questions on this example here? Okay, let's do another one. Okay, so let's do f of t is equal to t squared plus 6 cosine of 2t. Okay, so let's take the Laplace transform of this function. So let's take the Laplace transform of f of t. Okay. And so we're going to take the Laplace transform of t squared plus 6 cosine 2t. Okay. Okay, so once again, we're going to make use of the linearity property of the Laplace transform. So we have one function t squared plus another function 6 cosine 2t. So the fact that the Laplace transform is linear means that we can do it for each one of these individually. So let's take, or this is equal to Laplace transform of t squared plus Laplace transform of 6 cosine 2t. Okay. Good. So now that we have it in this form, we're just about there because the first term we have is Laplace transform of t squared. We know what this is. We know what this is already. So from the table, okay, we know this is equal to 2 over s cubed. Okay. Right. Then we have the Laplace transform of 6 cosine 2t. Once again, we have a constant out in front here, so we can take that 6 and just pop it right out because it's just a constant multiplier. Okay. And then we have Laplace transform of cosine of 2t. So cosine, the Laplace transform for that is, let me look back on the table up here. Okay. So the Laplace transform of cosine of 2t is s over s squared plus omega squared, where omega in this case is 2. Okay. So let's bring that down here. And so this guy is going to be s over s squared plus 2 squared, which is 4. Okay, so putting it all together, the Laplace transform of this f of s is equal to 2 over s cubed plus 6s over s squared plus. All right, any questions on how we did this, one here? Okay, good. Doing the forward transform usually isn't that bad. It's basically just matching up with stuff in the table. Okay. Doing an inverse transform is a little bit more tricky. Okay. So to do an inverse transform, we're going to make use of the table. But doing an inverse transform is a little bit more about pattern recognition. So kind of manipulating a Laplace expression to look like something in the table, and then using that table to perform the inverse transform. Okay. So to perform an inverse Laplace transform, basically we're taking a function in the Laplace domain and then transforming it back into the physical domain. Okay. So the unfortunate thing about the inverse Laplace transform is that there's no formula for this. It's really just about kind of algebraic manipulation and just kind of pattern recognition. Right? It's one of those things where you kind of have to, once you kind of do it, a few dozen times, then you start to get some really good intuition about it. When you're first starting out, it kind of seems like it's magical. Like it's like, how did you know? Like, how did you know it was going to be like that? But it comes with practice. Okay. So let's see how this goes. Okay, so let's start with a simple one. Okay. So let's say that f of s is equal to minus 2/5 multiplied by 1 over s minus 3/5. Okay. And what we want to do is we want to find the inverse Laplace of this function. Okay, because we want to transform this function back into the physical domain. Okay. Okay, so first thing we notice is that we have a minus 2/5 here, which is just a constant. And so this we can kind of mostly ignore, right? So inverse Laplace, just like forward Laplace, it is a linear operator. So we don't, we can kind of just take any constant the constants that we have and just take it along for the ride. Okay. Okay. And so what we want to do is we want to take inverse Laplace. So I use this symbol for inverse Laplace, which is the fancy L, the spaghetti L, raised to the minus 1 power. Okay. Of f of s is equal to, I'm going to take that minus 2/5 and just take it out just because it's a constant. And then we're going to take the inverse Laplace of 1 divided by s minus 3/5. Okay. All right, so to perform this inverse Laplace, let's look at our table of Laplace transforms and see if this looks like anything that we have in the table. So anything. So basically I have 1 over s minus a constant number, some kind of number, okay? Okay, so let's look at our table again. Now today's gonna be a little bit of whiplash because I'm gonna keep scrolling up to this table, okay? And let's look at the right-hand side of the table and see if there's anything there that looks like the function that we're trying to inverse Laplace, okay? All right, so it turns out there is. And in fact, it's perfectly exactly what we want. And so the Laplace transform of e to the at is equal to 1 divided by s minus a. Okay, that's exactly what we have because we have 1 divided by s minus a number, but that number in this case is 3/5. Okay. Okay, so to perform this inverse Laplace, we say, is there anything in the table that looks like this? Yes. E to the at. Okay. And so if we perform this inverse Laplace transform, we get f of t is equal to minus 2/5 e to the 3/5 multiplied by t. Okay. Any questions on how we did this example here? Okay, let's do another one. I just have endless examples for you guys. Okay, so let's say we have an f of s function that looks like the following. So we have f of s is equal to 4s divided by s squared plus 9. Okay. Okay, and then just like the last one, we want to find the inverse Laplace transform of this. Okay. So first thing we see is we have a 4 here, so let's go ahead and just factor that person out. Okay. And so our f of t is equal to 4 inverse Laplace of s over s squared plus 9. Okay. Every Thursday is just party time over Thursday, just random noises. Okay. So once again, let's look at the table and see if there's anything in the table that looks like this. Okay. So let's go up to the table one more time. Okay. So we have s over s squared plus 9. Okay. So it turns out there is something in the table that matches this, which is cosine. Okay. So the Laplace transform of cosine omega t is s over s squared plus omega squared. So that looks pretty much like what we have. Okay. Now you have to be careful here with the trig functions here because you know when the frequency gets transformed into the Laplace domain, they almost always get squared in the denominator. Okay, so when you're taking the inverse Laplace of this, you know it's not cosine of 9t, it's cosine of 3t because 3 is the square root of 9. Okay. Okay. So this inverse Laplace is equal to 4 cosine of 3t. Okay. Any questions on this one here? Yeah.
How do you know it's not negative?
So it could be -3. But usually the convention is just to use positive numbers for this. And then in terms of cosine, it doesn't really matter because cosine's an even function anyway. So if you do cosine of minus 3t, it's the same as cosine. It does matter for sine, but usually we just assume it's positive. Okay. All right, let's do another example. This one's a little bit more tricky. Okay, so let's say f of s is equal to 3s plus 2 divided by s squared plus 25. Okay, we want to find the inverse Laplace of this. Okay. So remember, inverse Laplace is a linear operator here. So we can first of all we can take that 3 and we can kind of factor it out. Okay. And we can take the numerator, we can kind of split it up into 2 as well. We're going to split the numerator. Since inverse Laplace is linear. Okay. All right, so let's do that first. We have f of s is equal to 3s divided by s squared plus 25 plus 2 over s squared plus 25. Okay. All right, so the first term here is pretty straightforward. So we kind of just did that in the previous example. Okay. So we know the inverse Laplace of this is going to be 3 cosine of 5t. Okay. So 3 just is kind of just carried through. It's just a constant. And based on the denominator, we know the frequency in this case is square root of 25, which is 5. Okay. Okay. Let's look at the second term. And so, this one's a little bit more tricky because sine is a little bit more tricky to work with. Okay. So if you look at the table, okay, we can see we do have a Laplace transform entry for sine of omega t. Okay. So the Laplace transform of sine omega t is omega over s squared plus omega squared. So it's similar to cosine in that the denominator is the same. The numerator is different. Okay. Now the numerator has omega in it just by itself, right? Which is just a constant. Right? And so you would think that we'd be able to take that function down there and just invert it properly. Okay. But here's where the table, here's kind of where the pattern recognition kind of comes into play. Okay. This table entry basically is telling you that in order to perform this inverse transform, the frequency of that term has to be in the numerator. Okay. So let's come back down to our example down here. Okay. And so from this expression here, from the bottom, we know that our omega or our frequency is equal to 5, right? Right? Because we can see that the second term, the s squared plus 25, the 25 tells us that our omega has to be 5 in this case. Okay. Now let's look at the numerator here. The numerator here is not 5. In fact, it's 2. So technically speaking, we actually don't have the table entry here for sine omega t, right? even though we are pretty close. Okay. So before we can perform this inverse transform, we have to manipulate this so that we have 5 in the numerator. All right, so here's where some of the kind of algebraic manipulations kind of come into play. Okay. All right, so we need to manipulate this expression so that we have 5 over s squared plus 25. Okay. This is what we want, because we can take this and we can take the inverse of this very easily. Right? But this expression that we have here is not equivalent to what we have above, because what we have above is actually 2 over s squared plus 25. Okay. So to make this equivalent, what we can do is we can actually multiply this thing by a factor out in front to make it equivalent to what we have above. Okay. So, when you're doing these inverse Laplace transforms, you can manipulate these expressions algebraically, but you can't change the numbers, right? So if you do something like this, where you're going to manipulate the numerator to be something else, you have to kind of compensate it so that it's still equal to the original function. Okay. Okay, so what can we multiply to out here to make it equivalent to above? What if we multiply by 2 over 5? Okay. And so if we multiply by 2 over 5, right? This 5 will cancel out with this 5, and we end up with 2 over s squared plus 25, which is what we had before. Okay. So this is good. But if we do it in this form, we can actually take that inverse of what's in the parentheses. Okay. Okay. So taking the Laplace, inverse Laplace of this entire thing, what we get is 2 over 5 sine of 3t. Okay. So we basically kind of factored out a 5 into the denominator in order to make this inverse transform work. Okay. So our final function here, f of t, is equal to, right? We had our cosines. We have 3 cosine of 5t. And I got this wrong. It's not 3t, it's 5t. Sorry for probably gave you guys some heart attacks here. So, and then plus 2/5 sine of 5t. Sorry about that, right? There was a typo, should have been sine of 5t. All right. Any questions on this example here? Yeah, so a lot of Laplace transforms, especially the inverse Laplace transforms, you're going to see certain examples worked out, and it's like, how did you know how to do that? So, so to take something like this and factor out a 2/5 so that you can make the numerator 5, it kind of seems like, it kind of seems like magic a little bit, but this is kind of one of those things where you practice a bit more, you'll start to kind of see these patterns. Okay. Let's see, do I have one more for you guys? I do have one more. Okay. Okay, let's do one that looks a little bit, it looks simple, but it may be a bit challenging, but we're going to do a bit more of the tricks like we did up here. Okay. So let's do f of s is equal to 1 divided by 3 minus 4s. Okay. And let's find the inverse Laplace of this. Okay. So this here looks kind of deceptively simple. So, it's there's no s squareds or anything like that. So we know it's not a sinusoid. Okay. This, in fact, actually looks very similar to our first example. And so this kind of looks like the transform for e to the at, because if you remember from the table, the Laplace transform of e to the at is equal to 1 over s minus a. Okay. So this kind of looks like that. It's not quite there, but it kind of has that that pattern. So we have a minus sign, we have an s and a singular in kind of a linear power down there. And there's a minus sign down there. So we can probably manipulate this to try to get it into this form. Okay. All right, so first thing we see is that we have 3 minus 4s. The signs of those things should be reversed, and so it should be s minus something. So let's pull out a minus 1 to kind of invert the bottom side. All right, so we pull out a minus 1, we get minus 1 or minus 1 over 4s minus 3. Okay. All right, so that's a good start. So we have our terms in the correct order on the bottom. But we're not there quite yet because the coefficient in front of s is not 1, and it has to be 1 in order to match with that form up there. Okay. So next thing we're gonna do, let's pull out a 4 from the denominator. To get the coefficient of s to be 1. All right, so we have f of s is equal to minus 1 divided by 4 multiplied by s minus 3/4. Okay. All right, so all I did was just pull out a 4, so I divided both terms there by 4, and then that 4 comes out. Okay. All right, let me rearrange this a little bit just to make it a little bit easier to see. And so we have a minus 1/4 multiplied by 1 over s minus 3. Okay. All right, so now we're in a spot where we can invert this, because if we look at our table entry for e to the at, okay, we have 1. This is 1 over s minus a. If we set a here equal to 3/4, then that is our transform. Okay, so now we can invert this. And so we have f of t is equal to minus 1/4 multiplied by e to the 3/4 t. All right. Any questions on this example here? Okay, good. Yeah, so there's a ton of examples, but honestly, this is probably not enough yet. There's something you'll just have to kind of practice a lot and kind of see a lot on your own. Once you kind of see the patterns, then things become easier. Okay. With that said, I'm about to kind of throw a wrench into this, and so we're going to learn kind of a technique that we can use with Laplace called the first shifting theorem. Okay. All right, so the first shifting theorem is a way, is kind of like an add-on to kind of everything that we learned with Laplace. It turns out if you multiply just a generic physical domain function by e to the at, what that's going to do is that it's going to shift your Laplace transform by an amount in the Laplace domain. Okay? So if you know the Laplace transform of a given function f of t, okay, i.e., we know that Laplace transform of f of t is equal to f of s, right? So either let's say that you know this from the table or you worked it out from an integral, okay? So you know your base function f of t, you transform it, you get f of s, okay? Then if you take your physical domain function f of t and multiply it by an exponential, okay, you actually can very easily get the Laplace transform for that as well. Okay. And so the shifting theorem goes like this. And so if you try to take the Laplace transform of e to the at f of t, okay. All right, so it's just a modification of your original function where you're just multiplying it by an exponential. Then the Laplace transform for this is you're just going to shift s by the amount a. So it's going to be equal to f of s minus a. So this is really convenient because, when we're solving our differential equations, a lot of times our solution is going to be some exponential multiplied by a function, right? So if you think of our mass spring damper, so, when we had damped oscillations, our solution to those problems was e to the at multiplied by sine or cosine, okay? Okay, let's do a very quick example just so you can see this in action, okay? So let's say that we have f of t is equal to sine of 7t, okay? Right. So based on the table, right, sine of 7t is inside the table, so we know how to get the transform of this. So based on the table, our f of s is equal to 7 divided by 7 squared, or s squared plus 49. Okay. Right. But with the first shifting theorem, what we can do, and so let's say that we have f of t is now equal to e to the minus 3t sine of 7t, okay? So something like that, we don't have in the table, or at least not explicitly, but we can make use of the first shifting theorem to modify our previous answer. And so the first shifting theorem basically says that everywhere we see s, we're going to replace it with s minus -3, s plus 3, okay? So it's going to be f of s is equal to 7 over s plus 3 squared plus 40, okay? Where in this case, we shifted s by 3 because of exponential. All right. So by itself, first shifting theorem is, I think pretty straightforward to understand. You multiply by an exponential, you just shift s, okay? It's just when you start combining it with all the other things, especially with inverse Laplace, things get a little bit tricky. But any questions on this example here? Simple. Okay, so let's do another example. This one's gonna be a little bit more challenging. Let's say that f of s is equal to 3s minus 137 divided by s squared plus 2s plus 401. Okay. Okay. And we want to find the inverse Laplace. Okay. So this is a fun one. So there's quite a few things going on here. Okay. Let me kind of walk you through kind of my own kind of thought process and kind of when, if I see a problem like this, kind of how I kind of start to attack. Okay. All right. So first thing I see is that in the denominator has basically a quadratic function. Right? So we have s squared there, we have an s and some constant, okay? Usually when you have a quadratic function down there, so not just s cubed or not just s squared by itself, but actually s squared plus something else, right? Usually this means that your answer is going to be, or your inverse Laplace is going to be some kind of sinusoid, so either sine or cosine. I should say sine and or cosine. So actually we're gonna have both in this case. Okay, so that's the first thing that I see. So first thing I see, we have quadratic function on the denominator. We're probably going to end up with sine or cosine. Okay. Okay. But if you look back in the table, there's nothing in the table that has something like this, right? And so everything in the table for sine and cosine is s squared plus omega squared, or s squared, it's either s squared. It's only s squared plus omega squared. Okay. So this thing actually has something else, which is an s term right here. Okay. So we have s squared plus 2s plus 401. Okay. So the fact that we have a linear term here, the fact that we have both s squared and a term multiplied by s, this probably means that we're going to have a sinusoid that's going to be shifted by an exponential. Right? So there's going to be a shift, okay? Because if you look back at the previous example, right? So the previous example, our result, or our Laplace result was 7 over s plus 3 quantity squared plus 49. Okay. If you actually FOIL out that s plus 3 squared, you're going to get s squared plus 6s plus 9. Okay. So the fact that we have a 2s here, which is kind of a term with kind of coefficient in s, probably means we're going to have some kind of exponential result. There's going to be some shift. Okay. Now, I'm going to do something that you probably, thought you would never use. Before I took a class like this, I legitimately thought I would never use this ever in my life. So let's complete the square on the bottom. My math teacher taught me this in high school. And I thought this is just a parlor trick. This is never going to have any practical use. Well, I was wrong. So we are actually going to complete this square. Okay. Okay. So let's do this. So we have s squared plus 2s. Okay. And we want to add something to this to basically make it so that we can get a quantity square. Now it's been a long time since I've kind of learned how I did it in high school. So probably you guys might have learned it a different way in your algebra and calc classes. But for me, I kind of look at this. The way I think about this is if I want to complete this square, I look at this number right here. Okay. So the number that's multiplied by the s term or multiplied by the linear term, my quadratic, and then I divide that by 2. Okay. Because eventually, when you FOIL out that expression, you're going to end up with 2 times that thing. Okay. And so we have s squared plus 2s. So 2 divided by 2 is 1. Okay. So let's add a 1 here. Okay. So by doing so, we can take this and then we've completed the square. Okay. And so this is going to end up being s plus 1 squared. Okay, that's good because now we have this s term kind of in a form which kind of looks like our first shifting theorem, just good. Okay. Okay, but this 1 that we got here, we can't just poof it out of nowhere. So we have to borrow this from somewhere. Okay. We can't just add 1 and expect nothing to happen. And so luckily for us, in the original function right here, we have a 401 that we can borrow. And so we can basically borrow 1 from that 401. Okay. Okay, so we're going to subtract 1 from that 401 so we can add it to here. Okay. So now our denominator, after doing all of that, is equal to 3s minus 137 divided by s plus 1 quantity squared plus 400. Okay. All right, and so if you look at our denominator now, it's in much better shape because that looks like a sine or cosine, but we've shifted it by 1, okay, by completing that square. All right, any questions on how we did that there? Okay, good. All right, but we're not out of the woods yet. So all we did so far was we kind of cleaned up our denominator, but we do still have to take the inverse of once. Okay? So to continue on with this, let's split this up into 2 different terms. Okay. And so this is going to be 3s divided by s plus 1 quantity squared plus 400 minus 137 divided by s plus 1 quantity squared plus 400. Okay. Okay. Because now by splitting this, we can see we have, first term here is going to be cosine because we have an s in the numerator. Second term there is going to be sine because we don't have the s in the numerator. Okay. Okay. This looks like cosine. This looks like sine. Okay, good. We're not quite there just yet, though, because from the denominator here, we can see that we have a shift in this product, right? So we're shifting our s by 1. So basically everywhere that we see s, we need to perform that same shift. We need to get it into that same thing. So the only other place where we have s is in the numerator of the cosine term. Right? So before we can take the inverse, we need to manipulate this. So that it also incorporates the shift. Okay. And so this is going to be equal 3. Okay. The 3 is just along for the ride. We're just keeping it through. Okay. So in order to get it to be look like the denominator, we did have an s plus 1 in the numerator. Okay. So that's s plus 1 squared plus 400. Okay. So now that term there looks good. So that term there, looks like we can take the inverse, right? But once again, we've kind of added a 1 in there, and we can't just do that out of nothing. So we need to make sure we are keeping this equivalent. Okay. And so because of this 3 right here, in order to balance that out, we need to subtract 3 divided by s plus 1 quantity squared plus 400. Okay. To compensate. And so because we added 1 to the s on the first term, we have to subtract it from the second one. Okay. And then we still have a minus 137 divided by s plus 1 quantity squared plus 400. Any questions on kind of why we did that there? Okay, good. All right, so we're just about done. So let's combine the 2 terms on the right. Okay. And so this is equal to 3 times s plus 1 divided by s plus 1 quantity squared plus 400 minus 140 divided by s plus 1 quantity squared plus 400. Okay. Now we can invert. Okay. So the inverse of this first term right here is going to be 3 e to the minus t cosine. So omega in this case, the frequency is 20 because it's going to be square root of 400. So that first term is 3 e to the minus t cosine of 20t. Okay. Minus. The second term is going to be sine because we don't have an s in the numerator. Okay. And remember, for sine, we need to have the frequency omega come out of the numerator. Okay. So the way we can do that is we can do minus 7. Okay. So I basically factor out a 7 so that we have a 20 in the numerator. Minus 7 e to the minus t sine of 20t. All right. Any questions on this example here? How we do this? All right. It's going to take some practice. I know, these things, even for me, it takes practice even now too, to kind of see the pattern. But you know, once you get used to it, it does start to get kind of pretty cool. We use the tables and to manipulate things algebraically in order to get things in the right form. So, you know, it's this, but taking inverse Laplace transforms is all about, you know, trying to find the pattern and trying to manipulate it in order to get it into that exact pattern. Okay. Okay, so for the last 15 minutes of class today, let's start to bring derivatives and integrals into the mix, or mostly just derivatives. Okay. So let's look at the Laplace transforms. Okay. Because if you remember from class on Tuesday, you know, ultimately our goal with Laplace transforms is to use them to solve our differential equations. So that means we're going to be basically taking an entire differential equation, taking its Laplace transform, and then, you know, and then kind of working it from there. So in order to do that, we need to know how to take Laplace transforms of derivatives. Okay. Okay. All right, so just like with the first shifting theorem, let's assume that we know the Laplace transform for a function f. So let's say that we have the Laplace transform of f is equal to big F of s. Okay. Right. So that's either known to you or at least you can represent it as F of s. Okay. Okay. So then the Laplace transforms of its derivatives are given by the following expressions. Okay. Okay. So first we have the Laplace transform of the first derivative, so df dt. Okay. Right. To take the derivative of f, the first derivative, we can find its Laplace transform using this formula. So this is going to be f s times big F of s, okay, minus little f of 0. Okay. All right, so the first thing you notice is that, you know, by taking the derivative and taking the Laplace transform, we're going to multiply the derivative, or we're going to multiply in the Laplace domain by s, okay? So that's one of the main strengths of the Laplace transform, is that we're essentially taking a differential operator, a derivative, and turning it into algebra. So we're multiplying by s, okay? Now, this term on the right is actually really interesting, okay? So this little f of 0 here is actually the initial condition on f in the physical domain. Okay, so that's why I use little f here. So that's really interesting, actually. So at the end of the day, you know, the initial condition is just going to be a number, right? It's going to be some constant or some value there. But it's interesting that that actually factors into the Laplace transform. Okay. Let's look at the expression for the second derivative. So the Laplace transform of d squared f dt squared. This is equal to s squared big F of S minus S times a little f of 0 minus f prime. Where once again, this little f of 0 and this little f prime of 0, those are the initial condition and the initial derivative in the physical domain. Okay. So this applies to this and this. Okay. So by taking the derivatives of our function in the Laplace domain, you just kind of end up multiplying by s. But then the kind of the main thing here is that the initial conditions kind of come along for the ride as well. Okay. All right, and this kind of has one important consequence. So when we take Laplace transforms of differential equations, which we are going to do right after this, or at least I'll show you. Okay. What's interesting here is that the initial conditions kind of just naturally get baked into the solution just automatically. Okay. Which is pretty nice, right? And so you can kind of solve the entire problem as kind of one problem set. Okay. That wasn't the case when we were solving our methods from before. So from before, if you recall, you're solving like a second order differential equation. First, you would find the homogeneous solution, which is your general solution, and then you would get your solution valid up to a couple arbitrary constants. And then you would then apply the boundary conditions or the initial conditions onto that and solve for the values of those constants. So it's kind of like a multi-step procedure. And it was even more kind of cumbersome if you had a particular solution as well, not homogeneous term. But with Laplace transforms, those initial conditions get baked right into the solution. So you don't have to do a separate step. It's kind of already there. And you don't have to do anything extra beyond just the extra algebra that you're doing. Okay. Okay, so let's apply this to a differential equation. Okay. So let's pick our second order linear ordinary differential equation with constant coefficients, and I'll even make it non-homogeneous. Okay. So let's do y double prime plus p y prime plus q y is equal to let's say our non-homogeneous term in this case is r of t. Okay. And let's say that we have two initial conditions, y of 0 is equal to k0, and y prime of 0 is equal to k1. Okay. So these are our initial conditions. Okay. So this is a problem we've seen many times at this point. Okay. So just like we usually do, let's solve for the solution to this ODE y of t, but let's do it with Laplace transforms instead. Okay. So if you're going to solve an ODE with Laplace transforms, there's kind of a three-step process to kind of follow for this. Okay. So first thing we're going to do is we're going to take the Laplace transform of the entire equation. We're going to take Laplace transform of y double prime plus py prime plus qy is equal to r of t. Okay. Once again, let's take advantage of the linearity of the Laplace operator. So let's apply this individually to each of the four terms. Okay. So we have Laplace transform of y double prime plus Laplace transform of py prime plus Laplace transform of qy is equal to Laplace transform of r of t. All right, so let's plug in expressions for all the derivatives here. Okay. So for y prime, we have s squared big Y of s. Now we don't know what Y of s is in this case, but we're going to solve for it through this problem. Minus s y of 0 minus y prime of 0. Okay. Plus p is just a constant here, so I'm just going to pull it out. This is p multiplied by s, big Y of s, minus little y of 0. Okay. Plus q. Q is just a constant, so we pull it out. Okay. And that's equal to y of s. Okay. Now, Laplace transform of R of t, we don't know what R of t is, at least not here. But generally, you know, for a problem, you're going to be given R of t. So I'm just going to replace that. I'm just going to have a placeholder for that for now. R of s. Okay. But generally, this is known. Right. You don't need a placeholder for it because it's going to be some sine or cosine or some polynomial that you can actually take the Laplace transform using the table. Okay. Okay, so we'll pause here just because we're out of time. But what we're going to do on Tuesday is, you know, we're going to take this expression. We can algebraically solve for y of s, and so we'll see how that's done. And then we're going to take that result and then perform the inverse Laplace transform. That's kind of our game plan with these kinds of problems. Okay. All right, but thank you guys for coming today. I hope you guys have a good weekend. Stay dry, stay safe. You know, especially driving out there, it's crazy. One of my friends just got into an accident, so you know, definitely be careful out there. So I hope you guys have a good weekend, and I will see you guys on Tuesday.
Guys, no homework, you know.
Oh yeah, of course.
Do I need to write like my name right here?
That's okay. Your name's on there.
Okay, thank you.
Yeah.
Professor.
What's that?
I had a question on the homework.
Sure.
On the last part for part C, it says, I did not give you initial conditions for this problem. Why does that not matter?
Yep.
Considering it's at steady state. I wrote, you just read it. Be like, I don't know if that's right or not.
Yeah, well, that's basically right. So when you're solving a steady state problem, usually you're looking at the solution in kind of long term.
Yeah.
And so in long time, usually the initial conditions kind of die off by then.
Okay.
So they usually don't play an impact on the long term.
Okay.
Pretty much what you.
Thank you.
Yeah.
So another question. Or like, yeah, right. For the sign. Yeah. Yeah, it can be sign post on. So we say these So RT in the center, that fits. That's basically.
And then you multiply by speed, and then when you multiply by two.
Have a nice weekend.
You too.
Maybe.